Dear students, welcome to the session on complex integration basics. In the previous chapter, we learned the definition of analytic function. A function f of z is said to be analytic at a point z0 if f of z is differentiable at every point in some neighborhood of z0. We have another definition. If f of z is analytic in a domain capital D, if f of z is analytic at every point of D. Now we are going to have some basic results which are very much helpful in problem solving. Suppose I am taking f of z and g of z are two analytic functions. Then sum of these two analytic functions is also analytic. Similarly, if you subtract this two analytic function, this is also going to be analytic because I can write this as f of z plus minus of g of z. And next, f of z into g of z is also analytic. The third one, composition function, that is f of g of z is also analytic. Let us take an example. I am taking f of w for a different notation, sin w, that is an analytic function, and g of z is equal to z square. This is also an analytic function. Now I am going to compute f of g of z, that is sin z square. It is very clear from the property composition of two analytic functions are also analytic. Therefore, sin z square is analytic. Next, there comes a big doubt. If f of z and g of z are analytic, then f of z plus g of z is analytic. F of z into g of z is analytic. The composition f of g of z is also analytic. What about f of z divided by g of z? There is a big question. If f of z and g of z are analytic, then f of z divided by g of z need not to be analytic always. The reason, if suppose my denominator g of z will become 0 at a particular point, then f of z is not analytic. Example, if I am taking f of z is equal to sin z, g of z is z minus 1. We know that sin z is analytic, z minus 1 is analytic. But if you take f of z divided by g of z, we have sin z divided by z minus 1. So at z equal to 1, the function f of z divided by g of z is not defined because denominator will become 0, so it is not defined. So at z equal to 1, it is not analytic. The reason g of z becomes 0 at z equal to 1. So f of z divided by g of z need not to be analytic always. Next, we are going to deal with the concept entire function. What is entire function? A function is entire if it is analytic for all z values in the whole complex plane. Let us see some examples. All the polynomials are entire functions. Z, z square, z cube, minus z, a z. All are analytic everywhere in the complex plane. So they are entire functions. Similarly, e power z, e power minus z are entire functions. They are analytic everywhere. In the case of trigonometric functions, sin z and cos z are analytic everywhere. Similarly, in hyperbolic functions, sin hz, cos hz are analytic everywhere. They are entire functions. And very obvious, constant functions are entire functions. Why we are dealing here? We are going to use this content in problem solving. Next, there comes a question. Is there any function which are not entire functions? Obviously, we say yes. Let us see some examples. A function, it is not entire if it is not analytic at some point. For example, if I take f of z is equal to 1 by z, at z equal to 0, the function f of z is not defined. Other than this 0, everywhere it is defined. So this is not an entire function. Similarly, we can say sin 1 by z, e power 1 by z. All these things have a issue at z equal to 0. Next, whatever the property we see for analytic function, it is also applicable for the entire function. If f and g are two entire functions, then f plus g, f into g, f of g of z are also entire. Some example we see sin z and e power z are entire functions, then polynomials z square, some a into z square minus z, all are entire functions. Now sum of entire functions is also entire, and product of entire function will give you again an entire function. Composition, suppose we take this pi z square and sin z. Sin of pi z square is an entire function. Similarly, cos of pi z square is also entire function. If you add this two, this is also an entire function. Hope you understand. Next, there comes a question. What happens when analyticity fails? It is not necessary that all the functions are analytic everywhere. There are some functions fail to be analytic at some particular point. As I said, the example 1 by z is analytic everywhere but except z equal to 0, because at z equal to 0 it is not defined. Such isolated failure points have a special name. What is the name? It is known as a singular point. What is a singular point? A function f of z is not analytic at a particular point A, but it is analytic except the point A on the neighborhood of A. Then A is called as a singular point or singularity of f. The example we see, f of z is 1 by z. F of z is analytic everywhere and it is not analytic at the point z equal to 0. Hence 0 is called as a singular point of the function f. Hope you understand, students. Next, let us see some examples. We'll try to find some singular point of the given functions. Here the given function is e power minus z divided by z minus 2. When you see the numerator, e power minus z is analytic everywhere. It is an entire function. But when you see the denominator z minus 2, we have to check, is there any singular point? To find the singular point, take the denominator and equate it to 0. So we get z equal to 2. So at z equal to 2, the function is undefined. Therefore, z equal to 2 is the singular point for this function. So this is not analytic everywhere. At z equal to 2, analyticity fails and z equal to 2 is called a singular point for the given function e power minus z divided by z minus 2. The next example, you can see the numerator is sin pi z square. We know z square is analytic everywhere. It is an entire function, and then sin z is also an entire function. Therefore, sin pi z square is also an entire function. So it is analytic everywhere. But when you see the denominator, we have z square minus 1. When we equate the denominator z square minus 1 equal to 0, we get z square equal to 1, z equal to plus or minus 1. So at 1 and minus 1, the function is not analytic, and it is analytic every other point other than plus 1 and minus 1. So z equal to minus 1 and 1 are the singular points for this function. Similarly, when we take e power z by z plus 1, e power z is analytic everywhere. When the denominator is equated to 0, we get z equal to minus 1, which is the singular point for this function. And finally, we have 2 divided by z square plus 1. We say constant functions are entire functions. They are analytic everywhere. So when you equate denominator to 0, we get z square equal to minus 1, z equal to plus or minus I. So z equal to plus I and minus I are the singular points for the given function. Hope now you are very confident to find the singular points from the given function in the problem.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.